Hello. We'll be talking about the periodic law and the periodic table today. This unit has been broken down into four separate groups. We'll first talk about the group 14 elements in part 1. That is, those elements that are carbon and those elements below carbon. The assessment criteria for the group 14 elements is to know the occurrence of and be able to compare and contrast the methods of extraction of these elements from the earth, to recognize the trends in chemical and physical properties down the group, to be able to explain the shapes of the molecules of the compounds, to know and understand trends in oxidation states down the group, to know and be able to explain the properties of the oxides of oxidation state 2 and 4, and to know and be able to explain the relative stability of the 2 and the 4 oxidation state in an aqueous solution. Let's take a look first at the trends in chemical and physical properties down the group, as well as some of the methods of extraction. Carbon compounds can be found everywhere. In grade 11 chemistry, we spent a good deal of time talking about carbon compounds. We will as well this year. Metal carbonates are found mainly in the mineral form. They're in large deposits around the world, in things such as marble, limestone, chalk, and carbon itself in many of the carbon compounds we wear and we eat, as well as remnants of marine animals that we use in our construction. Now, we've looked at chemical and physical properties before. Take a look at the table that gives some information about melting point. You'll notice that there's a fairly significant difference between carbon and silicon and tin and lead. In the carbon and silicon structure, we see more covalent bonding, which indicates a higher melting point to break those bonds. However, in the tin and lead, the structure changes from a covalent network to a metallic bonding kind of network. Now, this is compounded by the fact that many of the group 14 elements have allotropes of one another. An allotrope is a different crystalline or molecular form of a substance. We'll talk specifically here today about carbon. Carbon can be found in at least 3 different forms: graphite, diamond, and Buckminster fullerene. Buckminster fullerene was only discovered in the late 1970s. Tin has 2 allotropes. White tin is stable at room temperature and above, and gray tin is more stable below 13 degrees Celsius. Because of the nature of these allotropes, churches built during the medieval period in Europe that had tin pipes or pipes of tin for the organ or for water or for other reasons often had that white tin changed to gray tin because of the temperatures in Northern Europe. Let's take a look at carbon and its 3 allotropes, and let's see how bonding helps or explains the shapes of molecules. In graphite, each carbon is sp2 bonded to 3 others, forming a hexagon shape in parallel layers. Now, the angles between each of the carbons are 120 degrees. And so we therefore have weak forces that connect these parallel layers. That's why you can use a pencil that's made out of graphite. We're shaving off these parallel layers. They contain one non-bonded, delocalized electron per atom. And this allotrope conducts electricity like a metal. However, another allotrope, diamond, is not sp2 bonded, but sp3 bonded to 4 other carbons. It turns out to be tetrahedral with a bond angle of 109.5 degrees. All electrons are bonded in diamond, so therefore it's a non-conductor of electricity. And we all know what diamonds are used for. In addition to jewelry, they're used in tools to cut and grind. As I said, Buckminster fullerene was discovered in the late 70s. Buckminster fullerene are sp2 bonded carbons, in fact 60 carbons in 12 pentagons and 20 hexagons. Now Buckminster fullerene accepts electrons to form negative ions, and at normal temperature it can be used as a semiconductor. But if you mix it with potassium, you can create a superconducting crystalline material. All of these allotropes are the same element. You see by the bonding the change in the properties. Now let's talk a little bit about oxidation numbers. After silicon, the shift is to greater importance of the lower oxidation state. What does that mean? That means in silicon compounds, you're much more likely to have a +4 oxidation state than a +2. But as you go down the group, +2 states are much more stable than +4 states. And it seems that the elements seem to behave more like metals in the lower oxidation states. How do we know this? Well, let's take a look at some oxides and chlorides of tin and lead. The +2 chlorides of tin and lead are white. They have relatively high melting points, they're water soluble, and they have properties similar to a salt. Tin chloride 4 is a low boiling point benzene soluble liquid, and PbCl4 is a thermally unstable oil. So as you see, we've moved down the group and they tend to behave more like metals. And the +2 oxides SNO and PbO are more basic than the +4 oxides SNO2 and PbO, because the +2 metals are less able to polarize the oxygen ion. So the bonding ends up being more ionic. So trends in oxidation state are similar to the kinds of things we've seen when we talk about allotropes and how they change from different organization of the element. Now, the +2 and the +4 oxidation state in aqueous solutions is relatively stable. And in order to take a look at that, I wanted you to take a look at an example of something that has 4 oxidation states in its aqueous form. We're going to look at a vanadium oxygen oxidation states video. I hope this presentation has given you an opportunity to start you thinking about the kinds of ways you're going to be tested. The idea here is for you to have all the information about the topics that are assessed in one place. This is one of many podcasts that will be provided. At the end of each podcast, there are questions to start your thinking. These questions are intended to be completed individually. The questions you see below talk about fullerenes and inorganic identification. Again, these are designed to make you think